All right, taking a look at example number 3, it says, what is the work done between 1 and 3 meters? Now, this is a great kind of warm-up problem here for potential energy because, one, we have a variable force here, right? So for this distance, I only have a force of 1. For this distance, from 1.6 to 3, my force is 2. So if I'm trying to get the work done on this object, I can't just do work equals force times distance. For this one, I'm going to have to find the area. Now, it only wants to work between 1 and 3. So you guys can decide how you want to split this up. I'm going to go, we can go here. Okay, so I'm going from 1 to 1.6. So what is the displacement? 0.6. So good, 0.6 meters. What was the force during that 0.6 meters? 1 Newton. Right, 1 Newton here. And so therefore the work done is 0.6 joules. Okay. Now from 1.6 to 3, my displacement is 1.4 meters. And the force during that 1.4 meters is 2 newtons. So this equals 2.8 joules. So if I want to know that work done, the work done during that time, it's just going to be the sum. So this is 0.6 joules plus 2.8 joules equals 3.4 joules. Okay? Now I can tell this is not a spring because if I were displacing a spring from 0 to 1.6 even, my force would be increasing the whole time. All right? The displacement of a spring related to force, it's a linear relationship, F equals kx. So using that idea, let's come over here. And we want to get the work now done by a spring here in example number 2. So here's the thing. I have this graph coming over here. We're going to call this spot x. We're going to call this spot the spring force. Okay, so all of these are the spring forces, but that's okay. So I would like the equation for this line right here. Does anybody know what that is? What is it? F sub s, so that my spring force equals, so think Hooke's law, Kx. Okay? So this is the formula for the spring force. All right? Now, if I have this graph right here, all right, if I found the slope, so the change in the spring force divided by the change in the displacement, what is that going to give us? That's going to be the slope, but what is the slope of this equation here? K, good. All right, so the slope of a force versus displacement graph, a spring displacement graph, okay? The slope is going to give you the spring constant, all right? So the spring constant is in newtons per meter, right? Remember? So what would the slope look like for an object that is more, like the material of it is more massive than this spring? What would happen? Would the slope be greater than or less than? If it was a thicker spring. What's easier to move, a thick spring or a thin one? A thin one's easier. So if I had a thicker spring, what would the slope of this look like? It would be steeper, okay? So when you're looking at a force versus a stretch, it takes more force to get the same amount of stretch on a thick spring versus a thin one. Okay, so we have this. So let's take a look now at work though, right? So work is, since this is variable, remember work is the area under the curve, right? So that's going to be 1/2 the base. Well, the base is x. And the height is the spring force. Everybody okay with that? But we have an equation for the spring force. So this is 1/2 x times, what is the spring force equal to? Kx. So it turns out that the work done by a spring is equal to 1/2 kx squared. Now the work is the transfer of what? It's the transfer of energy. So if I take this and I stretch it this far, I have done this much work on this spring, yes? Now because I'm holding the spring here, guess what the spring has? Potential energy. How much potential energy? 1/2 kx squared. So here we have it. The potential energy of a spring equals 1/2 kx squared. Not to be confused with the force of a spring, which just equals kx. These are two different formulas. The force of a spring gives you a value in newtons. All right. The spring potential energy equals 1/2 kx squared. Okay. So the x value from equilibrium, we start here. When we stretch it or when we compress it, the distance isn't from the wall, you guys. It is from the equilibrium position. All right, so it's from the end of your spring, however far you for equilibrium. What do I know about the spring force versus the pull force? Equal and opposite. Excellent. Another thing that I want to mention is if you have your potential energy, because this displacement value is squared, it does not matter if you have a negative displacement from equilibrium or a positive displacement, because when you square it, you're going to get a positive number. All right, the spring constant is always positive, so the potential energy for a spring is always going to be positive. So for our last example here, we're taking a look at a spring, and what's happening is a force of 12 newtons is being applied to stretch it. Okay, so you have this force, it's a pull force. It's being pulled and it stretches the spring, so 12 newtons, and it stretches it 0.0225 meters. Well, that's great. But what it wants to know is it has this spring again, right? And it's compressing it, so it's squeezing it together, and it's pushing it, and its displacement here is 0.350. And it wants to know, you know what? If this is the same spring, I don't know the force here, but what is the potential energy of that spring? So what you're going to do is take a look at the formulas that we know. For this one, I'm trying to find the potential energy of the spring. So that is going to be 1/2 kx squared. And you say, hey, you know what? That's great because I know x, it's 0.0350, but the problem is I don't know k. However, in this first problem, I know the applied force. But wait a second, I have an equation for the spring force. Spring force equals the spring constant times the displacement. But I don't have the spring force, right? All I have is the applied force. But by Newton's third law, remember, our applied force is going to be equal and opposite magnitude to the spring force. So what's happening is my applied force is the spring force, and that's going to be 12 newtons. So if I want to solve for k, I just have to take my spring force and divide it by the displacement. Well, the spring force is 12 newtons. The displacement is 0.0225, and that's going to equal 533 Newton meters. So it's going to take 533 newtons of force to move this spring a meter. So that's our k value. Okay. Now once we have k, now we can get the elastic potential energy. So here's the thing about this though, and you do need to be careful. I can use this k in the elastic potential energy equation for this because these are the same spring. We're talking about the same one. So remember, every spring has its own spring constant, but since this is the same, I can go ahead and use this. So this becomes then 1/2 533 Newton meters times 0.035 meters quantity squared. So make sure you square that. When you plug that in, you get that the potential energy of this spring, when it's compressed 0.035 meters, is going to be 0.33 joules of energy. Okay? So notice again, this equation, this is for force. Okay? This equation is for potential energy. Force is in newtons, potential energy is in joules.